Okay, well, thank you very much. Glad to be here. Sorry I missed all the talks yesterday, but I hope to meet you and catch up on that. Okay, so this is about cuprates yet again, and I want to tell you about some recent progress in understanding the central problem of the pseudogap. So let me just review some of the basic experimental characteristics of what's called the pseudogap phase. So here's a famous phase diagram where you have superconductivity at low temperature, and then familiar Fermi liquid at high doping, an antiferromagnet at very low doping. But the big mystery are in these big regions here, the pseudogap and the strange metal. Today I'll just talk about the pseudogap. And what you see here is that there is some kind of metallic state, which often is correlated to some kind of fluctuating order, say charge order, charge density wave order, or superconducting order, or pair density wave order, stripes, many such things and spin density wave, many such things have been discussed. But all of those orders seem to clearly disappear at some temperature, above which this pseudogap and the characteristics I'll describe are still present. So what are the main features? One is that if you're on the overdoped side, then you see a beautiful Fermi surface of a single band. And if you count up the area of the Fermi surface, it's exactly what the Luttinger theorem would require. So the Luttinger theorem would say at doping P, there should be a Fermi surface of size 1 plus P, because 1 is for the half-filled antiferromagnet and P is the doping. And that's exactly what you see. Okay. But when you lower the doping and you lower the value of P, then this beautiful Fermi surface seems to get truncated into what are called Fermi arcs. So what are these arcs? So I'm going to present a theory of that, but this is what they're called, and it's quite a striking feature because in nobody's theory, which is self-consistent, do you ever get Fermi arcs. You can get pockets with low intensity at the back, and if so, are there pockets, and what is the low intensity due to? So now if you look in this region, so-called antinodal region, where there is no, so remember here there was a Fermi surface. So now we're going here, where there is a Fermi surface at high doping, but no Fermi surface at low doping, and ask what is the electronic excitation? There clearly is essentially none at zero energy, but at higher energy is what you see as you scan that wave vector. So this is what you get. So we're scanning this wave vector here along this direction. And if you're on the overdoped side, or if you're at very high temperatures above T star, then you see the red line. And notice the red line crosses the Fermi zero energy. And that's where the Fermi wave vector. So these 2 points here, what they call KF1 and KF2, are precisely these points here, these 2 points there. But when you lower the temperature or lower the doping, then you get this blue curve. And this doesn't cross zero at all. And it actually has a minimum gap here at some finite wave vector, which is in fact not the same as KF, as this paper emphasized. And that's that's the electronic pseudogap. It's a clearly formed gap in this region. It's quite large, 30 MeV or so. And if you go to exactly pi zero, then it's almost 75 MeV. And this green line is something that develops below TC. That's believed to be the pairing gap. So there's a clear difference between what's called the pseudogap, which is present all the way above to T star, and then the pairing gap, which only develops below TC. All right, so that's the basic characteristics from photo emission. But on the other hand, in recent experiments, the last 2 or 3 years, a totally different picture seems to be appearing from magnetotransport. So what you'd like to see are the famous quantum oscillations, because that's a the foolproof measure of a Fermi surface. But nobody's seen that, presumably because the experiments are really difficult. The fields needed are very high. What they have seen is a precursor to quantum oscillation, which is called angle-dependent magnetoresistance. So here you take a magnetic field and you put it at some angle to the plane. All the electrons are moving in the AB plane here. And then you measure how the resistance varies as a function of the angle. So, and then you model that through some Boltzmann equation, simple Boltzmann equation of electrons moving along the equal energy surface orthogonal to the magnetic field. And from that, you can read off how the magnetoresistance will change as a function of angle. So the answer depends very much on the kind of Fermi surface you assume. And what you see here is data and calculation, and they agree beautifully using the large Fermi surface. So this is in the overdoped side, where P is bigger than some critical P. On the other hand, if you go to P less than PC, then everything goes haywire. The data is here, and I think the dashed line are the different theoretical models. The large Fermi surface simply doesn't work. Neither do these electron pockets, which are present at very low temperatures when there's charge density wave order. But what does seem to kind of work are these hole pockets, which have not just the front side, but also what's called the back side. And in this particular paper, the calculation they're doing is based on having long-range antiferromagnetic order. Only trouble is there's no long-range antiferromagnetic order here at all. So it's a model that seems to work, but you don't quite understand why. All right. So that's the angle-dependent magnetoresistance. Oh yeah, what I was going to say is, in photoemission depends on what's called the quasi-particle residue. So you could imagine a situation where the quasi-particle residue is large in the front and very small at the back, and that would explain the photoemission. On the other hand, ADMR, where you're not taking any electron out of the sample, doesn't care about the quasi-particle residue. So it's not insane that there could actually be a backside because it's independent of the quasi-particle residue. Okay, and then very recently there's been this amazing experiment which has gotten us quite excited. It's something called the Yamaji angle. It's also measuring angle-dependent magnetoresistance, but now in a different material. This is the mercury material, and above TC, over here, right in the pseudogap, at doping of 0.1. And there, they see something called the Yamaji effect. So one special thing about the mercury compound is a very simple structure. It's just purely tetragonal with the layers right on top of each other. Now, if in this case, where you just have a simple cosine dispersion along the C direction, and a very small modulation, this is greatly exaggerated. Then there's something called the Yamaji effect, which is the following. So the electrons semi-classically will move on this orbit, which is orthogonal to the field. And various things depend upon the area of that orbit, okay, as you learn in semi-classical physics, as shown by Onsager. What you find is that for certain angles, a certain angle called the Yamaji angle, to first order in the corrugation of the Fermi surface, the area doesn't change. So if you slide in the C direction, then the area of this orbit orthogonal to the magnetic field only changes to second order in the warping. It's unchanged. So this means that there's no dispersion along the C axis. So it's a flat band. So at certain angles, you get a flat band, just like a Landau level. So if there's a flat band, you would expect the magnetoresistance in this direction to be very large, but there's just no tunneling along that direction. Okay, so that's called the Yamaji angle, and it's been observed many times in various two-dimensional materials, the organic materials, and And the amazing thing is that if you measure the Yamaji angle, you can read off the size of the Fermi surface. It doesn't depend on any modeling. All you need to know is the Yamaji angle and the spacing between the layers, the value of C, which you know to high accuracy. And that will give you the area of the Fermi pocket. So this is what they reported. They assumed an elliptical pocket. And here are their calculations as a function of angle of the magnetoresistance, again, from a Boltzmann equation. This is the data. And this is plotted in a way that shows you very clearly that there is a very special angle, which is this Yamaji angle. So from this Yamaji angle, which you can measure at different values of phi, which phi is the direction in the plane, you can read off the size of the Fermi surface. All right, so they came up with a number, approximately 1.3% of the Brillouin zone. So this is the first clear measurement of the Fermi surface size in the pseudogap, at this doping and at this temperature up there. And you have a measurement of the Yamaji angle and hence the size of the Fermi surface. Okay, so that's quite an exciting thing because now there's a number. And now I'm going to tell you about a theory going back 20 years where we predicted that number. So that's what I'm going to show you now. Oh, the other thing, another characteristic of the pseudogap, which if I have time, I'll also discuss, is the fact that if you go to very low temperatures and look at the superconducting state, then out here this looks, for all the world, just like a simple BCS superconductor, except the pairing is anisotropic. And as you go across in low magnetic fields, nothing much seems to change. So even here, we expect it to be an ordinary BCS superconductor. But there's one thing that does have a clear difference between overdoping in the superconductor over here as opposed to here, and that has to do with the structure of the core of the vortex. So on the overdope side, you can solve the Bogoliubov-Dijen equation for a D-wave superconductor, and that predicts what's now called the Wang-McDonald peak as a function of energy at the core of the vortex, and that's seen beautifully on the overdope side. But on the underdope side, it's not seen, and what you see is instead these period 4 modulations around each vortex core. All right, so that's the summary of old and not so old data on the pseudogap. And if I have time, I'll tell you about our latest theory where we think all of that falls into place. Yeah?
Just a question about the number that you said about the size. Is it for specific?
0.1, P equals to 0.1. So at the moment, there's only one doping. So these are experiments at 80 Tesla, and you have to get very nice crystals, and I'm sure they're trying to do it at other dopings, but it may be hard. Yeah, but I'm sure they are. We expect it to be proportional to doping. And even the theory gives you an answer proportional to doping. But okay. So now, should I go through all of this? Yeah, very quickly. So there are, of course, no shortage of theory of the pseudogap over the years. The earliest was, well, let's think in terms of some phase fluctuations of the D-wave superconductor. And that can kind of explain the Fermi arcs. But it has problems. When you get well above here, you should just see the large Fermi surface, which you don't once you're above TC onset. And there's no way to explain the magnetotransport. So in this theory, there are no pockets, there's only arcs. So it can't explain the magnetotransport. There are also theories based upon fluctuating antiferromagnetism. So these have an easier time explaining magnetotransport. So that's fine. But the area, which is now known quite precisely, doesn't work, as I'll show you. Okay, so these are some of the people I've worked with over the years, last 3 or 4 years at Harvard. Currently, Maine Christos, as of just a few days, is going off to Caltech for a postdoc. Pietro Bonetti is still at Harvard, and also Alex Nikolenko, my student, and various other people. I think you'll recognize Darshan, who's now at TFR. And very recently, I've been collaborating with a group at IMSC, Chennai, of Sayantan Sharma's group, and his students Harshit and Ravi. Okay, so let me present just some hand-waving theory of some of these measurements. And then I'll talk about, as much as I can, a more specific formal theory of it. Okay, so the key here is the Luttinger result and its extension by Oshikawa. So one of the most fundamental theorems, going back to 1960, of any Fermi liquid is that the area enclosed by the Fermi surface is the same as that of free fermions with the same symmetry. Okay, so and that works beautifully on the overdoped side. Then in 2000, Oshikawa gave a non-perturbative proof of this, which we can call as an anomaly matching argument. So there's a certain anomaly associated with charge conservation and translation, which you can compute on the microscopic level. It's just the density. And then that anomaly must equal the anomaly of the low energy theory. So if the low energy theory is a Fermi surface, you can compute the anomaly of the Fermi surface, and they should match, and that gives you the Luttinger theorem. All right, so that seems like, this is completely sacrosanct. It's non-perturbative, and this has to be obeyed. Then around 2000, we proposed that this allowed, actually, there's a loophole, which is that the anomaly, it could be that the low energy theory is more than that of a Fermi surface. There could be a spin liquid. And spin liquids also have anomalies associated with the filling of the electrons. If you have filling, it's very rigidly equal to something, again, the density, which is 1. And so the sum of the two anomalies, the sum of the anomaly of the spin liquid and the Fermi surface should add up to the Oshikawa anomaly. And this allows you to give new states of matter that we call fractionalized Fermi liquids. Fractionalized because there is a spin liquid which is fractionalized, and a Fermi liquid, well, because there's also a Fermi surface, so electron-like quasi-particles. Okay, so that's the state that I claim will do the job in essentially explaining all these experiments. Okay, so let's give you a simple cartoon picture of this state. So if you have an insulating antiferromagnet, of course, it's an insulator, there's no Fermi surface. If you have large P, then you have just essentially free holes. I'll talk in terms of holes rather than electrons. Then the area of the Fermi surface is 1 plus P, which is the total number of holes relative to the fill band, divided by 2, factor of 2 for spin. Okay. Then what about if you have an ordered antiferromagnet? Well, if you have an ordered antiferromagnet, then the density modulo 2 per unit cell is just P. And so the total area enclosed by the Fermi surface should be P. On the other hand, if you just do some simple calculation of free holes moving in this background, you get these 4 pockets. But really, it's not 4, it's 2, because the magnetic Brillouin zone is the dashed line, because you've broken a symmetry. So you have only 2 pockets, actually, and a factor of 2 for spin. So the total area should be P, and so you'll get P over 4, 2 for spin and 2 for valley. Okay. So the area for the antiferromagnetically ordered metal or the thermally fluctuating metal, because thermal fluctuations don't change the apparent area of the Fermi surface, should be P over 4. And you do see this in the ordered antiferromagnet. You go to very low doping, it's beautifully seen, pockets of area P over 4. Okay, what about more exotic spin liquid states? So the earliest type of states that people talked about are called a hole-on metal, where you've got resonating valence bonds, but you've also got these vacancies, which are called hole-ons, which can also move around, which don't carry any spin. So if this complicated state, if you don't know what the statistics of these hole-ons are, but in many models they're fermions, then if they're fermions, they have to form a Fermi surface in any metallic state. So again, by just simple geometric arguments, you can predict the size of the Fermi surface, independent of all the details of your state. And what's the area? Well, here, there is no magnetic Brillouin zone. There's no broken symmetry. But these are spinless. So now there are 4 valleys, if you had 4 pockets, and in many models you do. They're not necessarily at some geometric point, halfway between here and there. They could be at any point. But they're spinless. So there's no degeneracy for spin. There's a factor of 4 for valley, so that gives you area P over 4, which is the same as the spin density wave state, somewhat unfortunately. But anyway, so this measurement can't distinguish between this state and this state. Other measurements could, but this one, magnetotransport, can't. All right, finally, what is the state I'm talking about? So now we could imagine that this hold-on metal also has fractionalized spin-a-half excitation, these spin-ons. This costs a little energy to create. But you can imagine that in the ground state, each of these spin-ons goes near a hold-on, and they form a bound state. And then the ground state is, in fact, a Fermi surface of the bound states. So now this bound state is a bound state of spin-on and a hold-on. So it has charge E and spin-a-half. That's exactly the charge of a hole or an anti-electron. So these are essentially electrons moving around in a background of spin singlets. So this is the state we call FL star. And this state will have a Fermi surface. In everybody's theory, this bound state is a fermion. And then there are also spin-ons present because you could break the singlet bond and get spin-on. Okay, so what is the area of the Fermi surface here? Well, now there's a spin degeneracy. These are spin-a-half objects. And if there's 4 valleys, well, then the area should be P over 8. Okay, so that's different. And this is what the FL star state should have. So let's see. Yeah, there's the spin-ons that are also present in this state. So to summarize, the antiferromagnetic metal gives you P over 4, the hold-on metals give you P over 4, and the FL star gives you P over 8. And all these areas are very robust. I've just presented very simple cartoon pictures, but the answers are exact. There's no corrections in any 3 of these states to these values. So that's the remarkable thing. And of course, so here, just to drive home the point, in 2007, we wrote a paper emphasizing this area difference. It should be P over 4 for the antiferromagnet. This is a descendant of the FL star state, but the broken symmetry of the valence bond doesn't affect the Fermi surface. It should be P over 8. Okay, and of course, I'm sure you're calculating ahead. What is P over 8? Well, 1.3% is 1.25% is the prediction of P over 8, which is very close to 1.3 and quite far from all the other models. So, this P over 8 value, if it holds up through subsequent experiments, I would say that it's the best evidence yet for fractionalization in this pseudogap. Because any of the non-fractionalized models, including the spin density wave state or anything else, don't give you P over 8. Okay, I'm not saying it's good evidence, it's the best evidence. I think it's good, but okay. All right, so that's the simple model and the cartoon picture, and I have 25 minutes or something. Okay, so now let me give you an actual theory, which will allow us to also compute things other than the area. But any questions so far? Yeah.
Any other spectroscopic measurement, what would be the signature of this effect?
Well, so I will talk about the predictions for photoemission. Then there's neutron scattering. So neutron scattering would predict that there's lots of spin-on continua at higher energies. There is evidence for that, but I won't talk about that here. We're right now writing a paper making detailed predictions for what should appear in neutron scattering. Yeah, there's of course thermodynamic measurements. The spin susceptibility will be that of a small Fermi pocket. So so that's the first place. NMR was the first place the pseudogap was seen, was by a dive in the spin susceptibility that many of the models can get. Yeah.
It's not the rationale for the antiferromagnetic utopia.
Yeah.
But could you say what's the rationale for either the holon metal or the FL star? Because it seems to be doping.
Well, okay, so yeah, great question. So it is RVB. The holon metal is just doped RVB. This is the oldest RVB model where there were holons and spin-ons. And now the only thing I'm assuming that the holons are fermions. Now in Anderson's Basker's model, the holons were bosons. Then they wouldn't form a Fermi surface. So then there's no hope of explaining the MRG effect. I think in Kivelson's model, with the dimer model, these were fermions, spinless fermions. So this is just a fluctuating antiferromagnet. I mean, the difference between thermal fluctuating antiferromagnet that Pines and Chupukov and Schmalian studied is they're mostly thermal fluctuations. Here you have quantum fluctuations leading to fractionalization, and that gives you the holon metal. So that doesn't work. Now the FL star, you can ask why would the bound states form? Well, the point is that to create the spin-ons, it costs you energy J. So, because the spin-ons are fractionalized from the valence bonds, you break them apart. So it costs you energy J. But the binding energy of a spin-on and a holon is T. There's a bonding orbital of this thing hopping back and forth in this strong coupling picture. So as long as in a TJ model, T is much bigger than J, the holons are not stable. They will become electrons. The spin-ons are okay. The spin-ons are still there, but the holons will disappear. And the Fermi surface is made up of the spin-on-holon bound state. Okay. All right, the difficulty, so this kind of picture has been around for a long time, 20 years. The difficulty has been that no one's ever done a calculation where you take a spin-on, a gas of spin-ons, a gas of holons, have them form a bound state, and have the bound state form a Fermi surface. That's not an easy calculation. But I'm going to show you now a method that does that. Okay. So first let me talk about the Kondo lattice, where this phase is also possible and where it has been observed in experiments, but I won't show them, where you effectively have bound states. Well, you have a bound state of an electron in a spin-on forming. Okay, so here's the Kondo lattice model. You have two bands. There's a band of spins, this is so-called the F band in the heavy fermion materials, with some mutual exchange J1. And then they have a coupling JK, Kondo exchange, antiferromagnetic, everything is antiferromagnetic, to some conduction band of electrons where the density is P. Okay. All right. Now, we're going to assume that when JK is 0, that these spins want to form some spin liquid. I don't know, some Kiteo spin liquid if you wish. Okay, so then there are two possible states of this model. One is where JK is small and the spin liquid is stable, any spin liquid you like. And then the conduction electrons form their own Fermi surface. And this is the original model of FL star. It's a very simple state. All we were saying was this state was stable. It's not unstable to the Kondo effect. It just survives at 0 temperature as a new phase of matter, which at that time had never been seen, but now is seen in several experiments. But the more familiar state, which is present in essentially every fermion, heavy fermion, is the Fermi liquid, where you get large Fermi surface, where the spins of the Kondo effect runs off to infinity. And that means you get some hybrid quasi-particle, which combines both the F and the C. And then the Fermi surface obeys the Luttinger theorem. The size of the Fermi surface is 1 plus P, 1 for the spins and P for the electrons. Okay. This is the state I'm interested in. And this state, effectively, the spins kind of have bound to the electrons and become a large Fermi surface. So what's the theory of this? The theory of this is really very simple, going back to work by Coleman and Asa Arbach and Kathy Levin and the creed, and so on, is the following. You take your spins and you write them in terms of fermionic spin-ons, these F1s, and then you plug this ansatz in here, and you just do a mean field theory. Just factorize this into quadratic forms. And the mean field theory, so you plug that in, you factorize this term, and you also factorize this. You'll just get two bands, the bands of the C's and the bands of the F1s, and they will hybridize with this phi, which is really a Higgs boson, which carries the gate charge of these spin-ons. So when phi condenses, effectively the spin-ons become electrons, and you just get a two-band model. And if only the lower band is filled by the Luttinger theorem, the area of the Fermi surface should be 1 plus p. And if phi is 0, then you get the FL star state. And many papers have been written discussing this phase transition, which I won't do now. Okay, so that's the basic phase transition between the FL star state and the Kondo lattice model, and the FL state. Okay, well, it's just the condensation of this Higgs boson, which is the hybridization of the F and the C. Okay, so that's it for the Kondo lattice. It's really very simple. Basically, some of the electrons form a spin liquid. And for the Kondo lattice, it's very simple because you know which electrons want to form a spin liquid is the F electrons. But for the Hubbard model, that's a lot more difficult question. I can't just arbitrarily pick some electrons because they're all equivalent to each other. There's only one band. So how do you form a Kondo FL star state in a single band model? All right, so here's the trick, a very clever trick invented by Yahui Zhang, who's now at Johns Hopkins. He was a postdoc at Harvard. And the trick is the following. So you can think of this will seem a little unnatural when you begin with, but hopefully by the time I'm done, you'll think, oh, this is obvious. This is what we should have done. And it's really kind of a very simple method to make sure whatever approximation you're making, you're not violating the Oshikawa anomaly. There's been many, many papers that have tried to come up with a theory sort of like FL star, but which have violated the Oshikawa anomaly. So there's just a very simple rule. So we're going to add in some degree of freedom. It will seem like you're doing something strange, but no, we do this all the time. And there's a rule for the degrees of freedom that you add in. So I'm going to add a bilayer antiferromagnet, which has a trivial ground state. The spins form singlet and just the product of all of them. And this is decoupled to the physical electrons. I'm studying this model, and just sitting behind me are some ancillas, which I'm going to use momentarily, but for now, they're not even coupled. This is the model I'm going to study. And these ancillas have a very trivial ground state, just singlets, product of singlets. And this is the kind of thing actually we do all the time when you do a Hubbard-Stratanovich transformation. But you don't do it in the Hamiltonian language. That's effectively what you're doing when you're decoupling the Hubbard interaction into a scalar field acting on the spins times phi squared. Then the phi, which is a spin one object, is really the triplet excitations of these two spins. But it's easier to think the other way, to go backwards. I'm going to claim that this model, at least at large J perp, is equivalent to this model. There's a canonical transformation that can relate the two of them. And the two differences. One is that here these are interacting electrons with the Hubbard coupling U, and here these are free electrons. The other difference is now the physical electrons are coupled to the ancillas by an antiferromagnetic Kondo coupling JK. All right, so you can now do the Schrieffer-Wolff transformation and get rid of the triplet states here, and then you decouple the singlets, and you'll get back this. So this is a simple exercise. Just takes a few minutes. You just need 3 sites, and what you find is that you lower the energy of the doublet state here as opposed to the singlet or the doubly occupied state, and the empty or the doubly occupied states. And that gives you the value of U, jk squared over J perp. So by cleverly choosing JK and JPerp, you can easily make the U bigger than the T over here. Okay, so this is an exact mapping. Fine. But we're going to work with this model because it gives us a little more flexibility in writing down ground states. And in fact, it's the lower model that Yasir has been working on to write down actual wave functions for the Hubbard model, which has been compared to cold atom experiments, but I won't have time to talk about that. Okay, but what are the phases of this model? Well, this mapping is this is only valid at large JPerp. And at large JPerp, it's a very trivial thing. They just want you get back to where you started. You just get rung singlets, and then these will form a large Fermi surface. That's not what you wanted. But now, let's assume that we are allowed to look at the regime of small JPerp or large JK. So why would that be at all reasonable? Well, this JK is like a Kondo exchange. And if you just had a single spin coupled to a conduction electrons, we know Kondo exchange runs off to infinity. So let's imagine that under some renormalization, JK becomes large. Now, what I won't go into, and which is gone into in great detail in these papers, is that if you want it to really work when JPerp is small compared to JK, then you also need additional gauge fields to ensure the singlet projection and get rid of the extra degrees of freedom. I won't go into that because in the phase that we're interested in, those gauge fields are also Higgs. But near the transition, they becomes very important. All right, so what happens at small JK? Well, it's very simple. Large JK. Well, if at large JK, for a moment you ignore the bottom band, then what you have is a Kondo lattice, conduction electrons of density 1 plus p, other way around. Yeah, conduction of density 1 plus p, and spins of density 1. So if you now form the large Fermi surface state of the Kondo lattice, the total number of holes here is 1 plus p plus 1, which is p mod 2. And everything is mod 2 because you can always take away a fill band. So you have a small Fermi surface, which is like the Kondo lattice heavy Fermi liquid because of the mod 2. So that's what you want, okay? Now this small Fermi surface it obeys the Luttinger theorem for the Kondo lattice. Now, Oshikawa would tell you, for the Hubbard model or its related ancilla model, this violates the Luttinger value. So there must be a spin liquid. And that's the beauty of the ancilla construction. You don't have to even know about Oshikawa. All you have to know is that you added a trivial set of ancillas. There's a spin liquid, that's the bottom layer. It is there. And so you're obeying Oshikawa. And this spin liquid is exactly at filling 1. I mean, it has the anomaly of exactly 1 electron per site. And that's related to the fact that the area of this Fermi surface here is exactly p. It's not some other value between p and 1 plus p. It's really quantized by the anomaly of the spin liquid. And the spin liquid kind of is very rigid. It remains that at the insulator. So that was another difficulty in many of the early works. You started with a spin liquid and you doped it, and you started modifying the spin liquid in ways that are not really allowed. You have to keep it very rigid, and the ancilla does that automatically. So that's one sentence summary of my talk. Pseudogap metal in a single band model has two components that are well understood today. One is the Kondo lattice heavy Fermi liquid seen in hundreds of compounds, and the other is a spin liquid. Well, okay, seen in fewer compounds, but there are solvable models, gauge theories, and so on. Today we understand them very well. And now all you have to do to complete the game is to couple them. And I have about 5 minutes to tell you about the coupling. That does have some effects. Okay, so let me, however, for now, ignore the bottom spin liquid, which could be any spin liquid you want at this point. Just look at the top two layers. Well, the top two layers are exactly Kondo lattice model I already showed you. This is exactly the same in exactly the same notation. and I just have to study it for a different density of the C. So when you do that, you do get 4 pockets of area P over 8 for appropriate parameters, which you can, fit to the data. So these parameters are T1 and the phi. So those are completely determined by this computation, for example. And the area is exactly P over 8, not anything else. And why is it P over 8 versus P over 4? If you're doing a spin density wave theory, you'd be hybridizing 2 Fermi surfaces, the original Fermi surface of size 1 plus P, and one shifted by pi of size 1 plus P. Here it is different. One of them is 1 plus P, the other one is 1. And that's what gives you in the end is P over 8. Okay, so that's starting to look like the data, but not quite. There's still appreciable intensity at the back. No one's ever seen it. So is that just have to make this smaller or what? So this was a question that was there. This paper is from a few years ago. But of course, the Yamaji effect has given us, renewed enthusiasm for this model, even though this doesn't work at the moment. You can also look near the antinode where I showed you this dispersion, and you get exactly the same dispersion that comes out with no further fitting parameters. Yes?
Within this model that why is there an isotropic spectral wave?
It simply comes from the hybridization. So in fact, this is near the nodal point, but it's similar near the so this is near the antinodal point. The original one is near the nodal point. You have the top layer, which is the C band, and then you have the F1 band. And the front side is mostly C, and the back side is mostly F. So that's why it comes. It's also present in spin density wave theory. But now you see that the Fermi wave vectors of the F band is out here, the Fermi wave vector of the C band is here because they have different densities. And in fact, the other one we need to take whole lag to get the data to work out. And so the position of the minimum pseudogap is not the same as the Fermi momentum as was in this. So this paper emphasized the difference between Kf and Kg. And that's exactly what you get, the same kind of shape. So it all seems to work. At least of the antinode, it works beautifully. But on the nodal point, we're fitting the data, but there is definitely a backside. Okay. All right, so to fix that problem and address many other things, we need to actually couple it. You can't just take a Kondo lattice model. There is a spin liquid present. As Oshikawa requires there to be a spin liquid. So we have to now pick a spin liquid. Which spin liquid? Okay, this is now 30 plus years since the theory of spin liquid has been developed. We have solvable models like Kitaev spin liquid, which are the interesting ones for our purposes, which have one spin per site are the honeycomb lattice, but this is not a honeycomb lattice, it's a square lattice. And the square lattice, the whole spin liquid story has been very, very complicated, an incredible saga, which is now, I think, all coming together. And through some very beautiful work, which I will quickly summarize. So one of the earliest attempts was by Nick Reed and myself, where we wrote the spins in terms of bosonic spin-ons. And then when these bosonic spin-ons were condensed, you had the Néel state. When they weren't condensed, you had a U1 gauge theory of the low energy of these spin-ons, which turned out to be a relativistic complex scalar carrying spin up and down, coupled to U1 gauge field. This is called the CP1 model. But there were also monopoles to worry about because this U1 gauge field is confining. And then various Berry phases of monopoles, which are related to Berry phases that Duncan computed for hedgehogs on this side. We computed them on this side and found the same Berry phases. And we showed that as a consequence of these Berry phases, there'd be a broken symmetry, there'd be a valence bond solid state. And this is now seen in numerous studies of the J1, J2 model, that there's a valence bond solid. So, but this appears at very low energies. And so now the question is, perhaps near the transition, there is a spin liquid. And in recent years, there's been a lot of evidence emerging that there is indeed a critical spin liquid here. But the formulation of that critical spin liquid that I'm going to use goes back to Affleck and Marston, even before us, where they wrote the spin in terms of fermionic spin-ons. And there's a particular mean field theory that's mentioned in their paper, which has 4 massless Dirac spin-ons at these points. So this looks very, very different from the CP1 theory, but wait on that a minute. So you can also look at fluctuations about this massless Dirac fermionic spin-ons, and it turns out a very simple theory. It's just like our theory of strong interactions of massless quarks. There's 2 quarks, and it's not SU3 quantum thermodynamics, it's SU2. And this was, I think, already known to Ian Affleck, certainly even at that early time. But since then, there's been a lot of work trying to analyze the fate of this QCD theory. And it has 2 possible fates. One is that there's a critical conformal field theory. The other is it confines. And what was learned was that the confining phase of this theory is exactly the 2 states that obtain the bosonic theory. So that remarkable fact is summarized in this triality, which was first pointed out in the paper by Chong Wang et al. The citation is somewhere there. Between the CP1 theory, the Affleck-Marston theory of Dirac fermions, and the third formulation of an SO5 nonlinear sigma model with a k equals 1 Mazzamino term, which is a direct analog of the SO4 nonlinear sigma model in 1 dimension by Affleck and Haldane. All of these are strongly coupled field theories, and recently, especially in the fuzzy sphere work of Yin Chen He, there's a lot of evidence that this is actually an almost conformal field theory of a very significant length scale. So that's what I'm going to take for the spin liquid, because that's what's coming from numerical evidence and a lot of field theoretical work. And as we'll see, it has certain features that are exactly needed to fit the data. But I won't have time to go into that. I'm out of time. All right. So very quickly then, we start from the decoupled Kondo lattice and the spins. And you now you take the particular Affleck-Marston spin liquid in the bottom layer. And then you introduce another Higgs boson, B, which couples the 2 layers together by factorizing the exchange coupling. And now it's all about this boson B. So we want to write down some effective energy, which you can just deduce by symmetry. So here's what it looks like. I'm out of time, but happy to tell you more. And what we've done recently is just taken a kind of a Born-Oppenheimer theory. This is work with Sant and Sharma's group. Just did a Monte Carlo study of the SU2 gauge theory in 2 dimensions. We know this Higgs potential up to some free parameters. And then for each snapshot of B and U, you diagonalize the fermions, the spin-ons, and see what you get. All right. So here's one snapshot where you see all these vortices in the superconducting order parameter, and around each vortex there is indeed the kind of charge order. The feature of this theory, which is very much driven by all these anomaly matching arguments, is that it cannot have a trivial vortex core. It must have something else appearing, and if you choose parameters, that's a period 4 charge density wave. Okay, sort of like that. Then we can also do the fermion spectrum. Let me skip all of this. Yeah, so this is when you put in the thermal fluctuations of B, you go from the pockets to the arcs. That's what you get from the Monte Carlo simulation. Not so bad. So the other basic observation also seems to work. I think I will end with that. Thank you.
We can have one quick question, 1 or 2 quick questions. Maybe I can ask a quick one.
Yeah.
So the spin liquid you're considering is the critical spin liquid.
Yes.
But
yeah.
So naively, wouldn't I think that requires fine tuning rather than an entire?
Well, so it's over quite a wide range numerically. It has correlation lengths numerically of hundreds of lattice spacing. So what will, of course, now, the critical spin liquid is supposed to be here. Now, when I lower the temperature, it has to confine, unless you fine tune. But in fact, as far as we know, the critical spin liquid is not totally stable from the numeric. So it has to confine. Now, the insulator, I quickly reviewed, it confines either to the Néel state or the valence bond solid. The part that I skipped is in the doped material, when B condenses, it confines into the D wave superconductor. So in fact you get a D wave superconductor, not any other wave, and that the nodal points have certain properties, is very much linked to the spin liquid. It won't work with any other spin liquid. Well, may work with some others, but this one seems to be the simplest thing to try, and then it works. So the D wave is also a prediction of that particular spin liquid. That's not an old statement. People had talked about that already in the 90s. But what we get in addition is that the velocities of the nodal quasiparticles in the two directions are very, very different. That was not the case. That was a big problem in the early days.
Let's thank Subir again for the talk.